Thank you. So welcome to the session. I'm going to be talking to you about Azure Data Lake Store. Before I do so, let me acknowledge the people who really built it. First and foremost, the storage team and the big data team. Bhaskar, can you just stand up on behalf of the team as a whole? So they really did all the work, and in collaboration with multiple organizations at Microsoft, including MSR and Sizzle. So a great thanks to all of them. Let's get going here. This work is grounded in the reality we live in every day with the Cosmos system, right? The same group also manages this internal service at Microsoft. Virtually every part of Microsoft uses this service for production every single day, right? And it includes, Bing for search, the ads platform for targeting delivery, Xbox, Office, Windows. There literally isn't a part of Microsoft that isn't fundamentally dependent on Cosmos. Right? The volumes reflect this. Thousands of internal developers, hundreds of thousands of production jobs a day, individual jobs that span thousands of nodes. Every day, literally hundreds of petabytes of I/O, a total managed base of multiple exabytes and growing, right? And there's only continual increase in the demands that are being made on this, as I'll say in a moment. So first and foremost, we needed a system that would be the next generation of Cosmos. With all its virtues, Cosmos is not fully a compliant store. There are various gaps we need to fill. Like every large successful system, it was time for a major rewrite. So what did we learn in thinking about this from Cosmos? First off, as a hyperscale service intended to deal with our internal customers, it needs to be of correspondingly large scale. We are also seeing a clear demand to multi-tenant, not just batch jobs, but batch interactive and streaming jobs. Right? In response to this, among other changes we have made, the whole thing is now managed by Yarn, and we are running multi-tenanted workloads on top of it. That's not something I'll be able to talk about today, but ADL, all up, the analytics part and the store part are designed to work in close complementarity. We need to be able to have BCDR in the event of failures in a given location, therefore geo-replication. For a single job, you may need to burst up and get pretty much all the bandwidth you can deliver, while at other times, individual jobs take somewhat less bandwidth apiece. You need flexibility in apportioning the bandwidth at your disposal. Most importantly, customers love the fact they don't have to worry about managing a cluster. It is a PaaS serverless service. You come in and you say, create a file, put this data in the file, run a job over a file, give me the result and the bill. They love it. But we are not 100% there, to be honest. Underneath, we still have physical clusters. And while we have hundreds of thousands of servers, and each cluster is tens of thousands, there do come points in time when a physical cluster is full. And at this point, it becomes apparent that there is physicality underneath. We need to migrate. We need to involve customers. It's a royal pain in the keister for our customers and for us. So to operate something like this at scale, everything has to be seamless in terms of migration and rebalancing. To get there required a major design rewrite. Okay? In particular, we needed a completely logical namespace. Along the way, we decided to make it a POSIX file and folder hierarchy. It needs a complete separation of the underlying microservices that manage the metadata from the physical clusters where the data is. These kinds of changes go very deep, and effectively we did a complete rewrite of the system to accomplish this. Next, and this is perhaps the single defining attribute of the re-architected system. On the one hand, with interactivity, streaming, GPUs, machine learning, deep learning, there is this demand for having data closer and closer to the CPU. flash, DRAM, main memory, hard disk, local disk, right? SSDs. On the other hand, the volumes of data are such we need to be able to store data that's not accessed so frequently, inexpensively. And this means moving the data to very different parts of the memory hierarchy. And you need to be able to do it without crossing compliance boundaries, right? You need to be able to do it without very much manual intervention from users. So to have high-level policies and to be able to let the system manage this transparently under the hood. And if, for example, something you need is not in the right tier, to have that be faulted in gracefully with minimal performance degradation. These were objectives we built to from day one, right? Lastly, when data is in the compute tier, it is absolutely essential to co-locate compute with the data, right? If you look at the span of how these systems have come about in the last 10, 20 years, the basic idea has been spray the data out, spray the compute out. Now, effectively, it becomes two-dimensional. There's also a memory hierarchy. You spray the data out horizontally and across the memory hierarchy. But still, when the data is close in the compute tier, you do want to co-locate your computation with the appropriate data, right? Finally, we were lucky in that we weren't starting from scratch. We were able to take some really core, well-proven Paxos implementations from Cosmos, marry it to state-of-the-art columnar processing from SQL Server Hackathon in rebuilding some of our core services. We were also able to build on and leverage some of the things we'd learned and built over the years as user-facing idioms. So one example I have here is when you have multiple files that are output at the end of the job, through metadata operations, very efficiently, we can stitch them together into a single file. Why is this important? Well, at the end of the day, one of the true bottlenecks in these distributed systems is metadata management, and the name node, for example, is a known bottleneck in HDFS. We attack this on multiple fronts. The underlying technology for metadata management is very scalable. We also work not to proliferate the number of files needlessly, right? We also have technology in terms of debugging and program development on the programming side of things, which we carry over, but I will not talk about that today. So what is ADLS at the end of the day? We made a core decision that not only would this be our next generation internal big data service, it's also the basis of what we are offering externally. One little caveat, the system I'm describing today exists, but not all the features exist in the publicly available version. They will be in a while. It is the first serverless PaaS cloud service that supports the full HDFS API. With all due respect to some of our friends in other companies, having remote blob storage with a web HDFS REST endpoint is not the same, right? Tiered storage with co-located compute, it actually delivers on this, and the co-location is accomplished, as I said, through Yarn. We are probably deploying the largest fleet of Yarn serving today, right? In fact, Apache 2.9, we are managing the release of Yarn. RSL HK rings, this is one of the technological innovations that was made possible by the fact that we were privy to a Paxos implementation and Hackathon rings, right? This is the foundation of all our metadata services. And security, while I will not talk a great deal about it, it is something we have built from the ground up. And you will see authentication based on Active Directory. You will see RBAC, file and folder level POSIX ACLs. You will see full compliance, SOC, ISO, and so on. And encryption, at rest, on the wire, with keys that we manage or a client can manage. One thing I want to underscore, what does it mean to be a full-fledged HDFS service? First off, it's a full-fledged file service. Folder operations are supported at scale with full fidelity. Not only that, implementation of operations like flush are optimized. And lastly, but most importantly, for HDFS, the operations, the API calls that allow you to co-locate your computation with where the data is, the ones that are called by the Yarn AMs, these are fully supported. Okay? Now that we have covered what ADLS is, let's go look at the architecture briefly. A file is pretty much what you would expect in most of these systems. Series of extents, and each extent is a series of blocks. Blocks are the unit of read-write. And when you look at this, the one new variant we have introduced is the concept of a partial file. A partial file is really a mini file, a subsequence of a file. But this gives us two benefits. One, it can be the unit of moving data and managing data across tiers, right? The other, which I will not talk about a great deal today, these systems are traditionally append-only. Our design is to support updates as we go along. And by making partial files splittable, mergeable, we give ourselves a ton of flexibility towards that end. Okay. One last point I need to make here. Our tiering framework is designed to be extensible. We can take a new storage platform and allow for data to be there and seamlessly accessible through ADLS by writing a quote-unquote storage provider implementation for that store in terms of storage provider APIs that are native to ADLS. So tiering, here's an example of the flexibility we have. If you take the blue line up top, that's a file with 4 extents in it. The very last, the tail which is being written to, right, it's in SSDs. That's the red block you see over there. However, blocks are being spilled to other tiers as we go. And on the local tier, you see 2 extents. These are really 2 partial files of an extent apiece, right? And on the remote tier, the first 3 extents have already been archived. You don't necessarily have to do this. The local tier is perfectly durable all on its own, but you could see something like this. So any part of a file, possibly redundantly, could be in any tier. What is stored where is a matter of policy, right? Here's the overall architecture. To summarize all this, what you see in the black is the fleet of machines where you can have local storage, HDD, and SSD today. These are also the machines where you have the cores that are allocated for compute using YARN. The YARN-based stack can use the HDFS get block location API to find out where the data for a given job is in doing this allocation. And because we use the standard sockets of YARN and HDFS, pretty much anything that is in that ecosystem, Spark, Hive can run on this fleet. In addition, our own internal tools, Scope, which is the workhorse SQL dialect on Cosmos, and uSQL, which is the T-SQL aligned version of Scope that is in the external service, both have been refactored to run on top of YARN side by side with the open source components. Okay, the one other point I want to make here, if you take the ADL microservices, while they run in the compute tier, they run essentially as abstract microservices through APIs, and they are not in any way, shape, or form tied to the physical location, unlike in Cosmos. Okay, one thing I want to emphasize here is the RSL HK ring and just how fundamental it is to us. What it is fairly straightforward. If you think of the name node, it contains an entry for every block of every file. When you think about this, the numbers can quickly get enormous. HDFS systems start to run into scalability problems with a few thousand nodes. In our system, we have clusters that are tens of thousands of nodes, and we anticipate growing even further. In fact, our design point here, remember, is to be agnostic to cluster boundaries. So really, we're talking hundreds of thousands of nodes already. Those are the scales. So we needed something fundamentally different to be able to handle this. We went to Hackathon. So if you take Hackathon, on a single node, we are able to get pretty good performance for table management. We provide this as a building block for people, for developers of metadata services, but this does not give us the high availability we need. For that, the state in a Hackathon node is replicated across 7 nodes in a Paxos ring. And there are many, many rings, and we can shard seamlessly across rings. Okay? If you take this combination, it is incredibly powerful. And every single one of our metadata services, the naming service that supports the extremely efficient directory operations and the name, the logical to physical lookups, that runs on top of this. The equivalent of the name node, the extent management service, that's layered on top of these. Think of all of these microservices as essentially being app logic that use Hackathon to do it, Hackathon transactions. And underneath, RSL takes care of all the scale and availability issues. Okay? Secret management, on and on. There are many, many microservices. Every single one of them rests upon the foundation of RSL HK rings. Here's a picture. The naming service, the extent management service, the secret management service, the partial file management service, the tiered policy manager, on and on. They all build on Hackathon. There's a fleet of gateway machines, but the more heavy-duty part of the environment is the fleet of machines on which we have storage. We have multiple storage providers that are seamlessly abstracted from the point of view of the user. These are also the places where the jobs run. This co-location is really what I want you to take away from this picture. Let's keep going. The secure store service. I won't have time, I'm afraid, to go through all of the services in detail. I'll hit on the high points. I urge you to read the paper for details. The secure store service is the point of entry into ADLS, right? This allows us to also make it a security boundary and provide differentiated APIs. For example, if you're writing a user program with user code, we don't want to expose the same APIs that we do to internal services, right? It orchestrates all the complex machinery underneath and gives end users an extremely simple API. The extent management microservice, this is the heavy lifting, right? The scale here is monstrous even for Cosmos. We have designed this to be an order of magnitude larger than all of Cosmos put together, right? And the performance we get, the throughput is way better while delivering better latency. All of this ultimately is due to the underlying RSL HK ring infrastructure. I'll present a few numbers at the end, but that's the takeaway. It is the authoritative source for file length, block location, file expiry, pretty much all the key file properties at the finest granularity of a block. Partitioning, of course, is the key to making this scale, and the APIs are fully transactional. Okay. The naming service. This is the thing that allows us to have a logical namespace, and this is one of the huge differences that we had to bridge in going from Cosmos to ADLS. Okay? It supports a truly hierarchical namespace with strong consistency in the operations and scale out, again, RSL rings. There are several other microservices that I will not talk about except briefly. The secret management service manages secrets securely. This is important because everything is encrypted in transit as well as at rest. The partial file manager, I already alluded to this briefly. One thing I should point out, we heavily optimize the storage of temporary data, right? And this is for performance reasons. And speaking of performance, let me talk briefly. We are designed to deal with petabyte scales. An individual file can be well in excess of a petabyte. There are tens of millions of files per individual account. There are no limits, right, on either number of files, size of files, or the throughput. Individual jobs can access as many files as they choose. We can actually control the throughput we deliver to a job or an account, right? And as examples, a single file was able to upload at a sustained throughput of about close to 200 Gbps. Why 200? That was the limit we set for that particular account, right? And that same account for a uSQL job, an arbitrary execution of a SQL-like job, we were able to deliver about 133 Gbps with the same quota of 200. And let's look at two more numbers, two more sets of numbers. On the right, you see the numbers for the extent management system. These most closely reflect the performance of the RSL HK rings. There are, if you look at these rings, these numbers reflect what you get from a single ring, which basically means a single machine, because all the machines in a ring essentially do the same thing. Okay? At a single machine with 150,000 read QPS, 50,000 write QPS, we are able to keep the 99th percentile within a few hundred milliseconds. In practice, that's just a stress test. In practice, we manage the numbers to be within 1 millisecond read, within 10 milliseconds, single-digit milliseconds usually for write. On the left, you see what that means for the naming service. If you take operations like naming or moving files across directories, again, the numbers are extremely small and, more importantly, not very variable. That turns out to be super important to us in practice, right? Again, our goal is to stay with single-digit milliseconds for reads and writes. Let me summarize at this point and leave a few minutes for questions. The bottom line is we have sought to build a scalable and reliable cloud file system. This, we are already migrating our internal workloads, and it's already a GA service. Okay? And you will see many of the features I've talked about, some of which are not available, flow to the external system in short order. We support open source. We work extremely closely with the open source community. If you look at authentication, it is strongly aligned with Microsoft's Active Directory. Tiered storage is our signature feature, one that we've really invested fundamentally from day one. The system is supposed to support batch, streaming, and interactive, and we are already operating in this mode internally. So with this, let me pause, take questions.
Here we go. So the tiering that you do on the caching at the higher level, like SSDs and so on, so data close to the computation, how much semantics is really there? Like, when you look at the join of big tables, so we want to co-locate the operands of the join.
Yeah. So at this point, the tiering that we have implemented, they are focused on the mechanisms, right? And to your point, there's a lot of work to be done in terms of taking advantage of semantics for intelligent policies. We haven't even scratched the surface there. Actually, Hiro, who's going to be talking about tiering as well, worked with us in the early days. I'm hoping he'll have something to say on this. Yes. Other questions? Yes, in the back.
Okay, so co-locate the compute and the storage definitely gives like the benefit, right? But on the other hand, I feel seems the recent trend is also like make the tiered system on cloud, like make the storage system more like independent. So now make the layer above it kind of really have no control of like the kind of the location of the storage. How do you I would like to get your comments on like these two things. They seem conflicting to each other.
So it's a great question. Fundamentally, I think if you want truly high performance, you need to be able to control co-location. At the same time, as you point out, if you want true elasticity, you need to decouple the two, right? And ultimately, you need to have policy-driven mechanisms. To Hamid's point, I think getting to intelligent policies is an area where there's a lot of room for work, okay? But ultimately, my core belief, you have to be able to manage this at the system level. This is too complex for users to even come near. And furthermore, these systems have sensitive data. If you have two systems across which you are manually moving data, it breaks all kinds of things in practice, compliance, for example. So this area is one where I think our database tradition of managing memory hierarchies, we really need to deliver.
So let me just ask you one question. How about fine-grained access, especially updates? Do you think that's something?
Yes. So historically, systems like HDFS have not supported fine-grained update, nor, to be honest, does the system I just described in its current incarnation. But already we have baked into the design features like partial files, specifically because we know that's something we are going to have to get to, right? And ultimately, I think all of the systems to the extent they don't support updatability, there are going to be large swaths of applications that you simply will not be able to support. So that's another area where I see lots of room for richness. Earlier today, we heard about HTAP. That convergence, systems designed for brute force analytics, also getting closer to supporting the attributes needed for warehouse kind of applications and eventually OLTP kind of applications. I see that happening. Yes?
What is the maximum throughput that the Paxos suite can deliver?
The maximum throughput. So we measure it in terms of number of operations per second for the kinds of 1 kilobyte read-write operations. And if you look at the numbers I gave you, a couple of 100,000 QPS per machine per ring, right? And then on top of that, you can have as many rings as you want. So in effect, we can scale to whatever we want. We take care of the partitioning on top. Yep, exactly.
All right, I think we got to move to the next song. So let's thank the speaker again once more.
Thank you.
Thank you.
All right.
Okay, so as we're preparing, so the next talk again is going to be another distributed file system, and it's going to be from University of Cyprus, and Herodotus is going to present it.
All right. Good morning, everyone. It's interesting how most of the questions addressed to Raghu could have easily been asked at the end of my talk to me. So I'm glad Raghu already answered them. Well, except that one. OK. I'll keep that in mind. Well, all right. So today we're going to talk about Octopus FS, a new distributed file system that promises to offer tiered storage management. Now, before we dive into the details of this particular file system, let's think a little bit about the current landscape of large-scale data processing systems, right? So think about Hadoop and its ecosystem with Pig and Hive. Think about Spark and Flink and so on. What do all these systems share in common? Well, first of all, they all run on large clusters of commodity hardware, and we've seen lots of improvements recently in terms of larger memory, new types of memories, NVRAM, phase commit, and so on, cheaper SSDs, and so on. Second, all these systems execute different types of workloads, which of course leads to a diverse I/O patterns, right? So MapReduce is typically batch processing, machine learning algorithms are typically iterative, and so on. Third, most of them process data on distributed file systems such as HDFS or GFS and MapR. Now, of course, we're not the first one to notice all of this pattern. There's a lot of work over the last 3 to 4 years that they take advantage of the improvements in storage tiers, either by explicitly storing data in memory and SSDs, or by caching data in memory from local disks or from disks from remote storage and so on. Now, in our setting, we would like to take a more comprehensive view and look at all the different layers together in a distributed setting. So our goal was to design and build a distributed, multi-tiered file system that is aware of the storage media with different capacities and different performance characteristics. Now, we want it to be distributed so it can run on clusters of commodity hardware along with the rest of the systems. We want it multi-tiered so we can actually exploit the heterogeneity of the available storage media. We wanted a file system to maintain the prevalent file abstraction that all the other systems are also using. And finally, we're stressing out performance characteristics because we would like to make automated decisions based on them. Now, this awareness of the storage media We argue that they're fully exploited once the system is capable of providing two competing capabilities, what we coined as automatability and controllability. Automatability means that the system should automate data management decisions. That is, it should automate where to place the files and the file replicas both across the nodes and the storage tiers in order to maximize throughput and cluster utilization. Controllability, on the other hand, means that the system should explicitly expose the storage media to the users, allowing them to choose the distribution of placement of replicas on the cluster based on their own performance and fault tolerance requirements. Now, in the world of automation, you may ask, why do we focus on controllability as well? The short answer is because that will actually allow other systems sitting on top to implement their own forms of automation, right? And that will become apparent towards the end of the talk. Now, the architecture of Octopus FS is inspired by the typical architecture of HDFS and GFS. In fact, we've built Octopus FS by making some significant extensions to HDFS. So as such, right, so there's a set of master nodes which are responsible for handling the metadata operations, right? So the directory namespace, for example, it's a file system, so we have directories and subdirectories and files. These files are broken down into blocks, which are replicated and distributed on the worker nodes. Now, the worker nodes are in charge of storing the actual data of the files on the different storage media that they handle. Now, the storage media are logically grouped into storage tiers. Now, I emphasize the word logically here because we actually do the grouping based on the I/O performance of the devices, not the devices themselves, to cover essentially cases where a cluster may have nodes, may have storage media of the same type, but of different performance, right? Which is fairly typical as clusters grow and newer hardware is added into the cluster. So for example, let's say we have a bunch of SSD devices across the different nodes, the same performance. All of them together will form what we call the SSD tier. Now, the files, like I said, they're broken down into blocks and they're replicated both across the workers and across the tiers based on either client requests or based on automated policies. Right. So let's start from the client requests. So the client exposes APIs for all the typical file system operations, create the directory, create a file, read a file, move a file, and so on. And in addition, similar to HDFS, the file system exposes the locations in terms of workers and the storage tiers of the different blocks. Now, all the APIs that deals with the files are actually take into account this new notion that we have added of the replication vector. The replication vector essentially specifies the number of file replicas on each storage tier. So if we take as an example, I guess the cluster that I have here, this one has 4 tiers: memory, SSD, hard drive, and remote storage. Our replication vector will have size of 5, 1 for each of these tiers, plus 1 more indicating the number of what we call the unspecified replicas. Now, we're starting to see where this controllability versus automatability will come into place, right? So when the file is created, the user can specify a replication vector, right? So they can, on one hand, they can fully specify that I would like to store my file on, let's say, 1 copy in memory and have 2 copies on the HDD tier. On the other extreme, maybe the application doesn't really care about explicitly specifying the location of the replicas. In this case, they can use the unspecified location to say, hey, I would like for this file to be stored with 3 replicas, and let the system decide. And of course, we can achieve anything in between. For example, we could say, hey, I would like a replica of my file in memory, and then 2 more replicas. I'm going to let the system decide where it's best to actually store those replicas. In addition, there is a single API that can be used for modifying the replication vector and achieve an array of different types of operations, such as copying a file within a tier, or deleting from a tier, or copying and moving it across tiers. All that with just a single, very simple API. Now, right, so the client, let's say they've created their files or they've changed the replication vector of a file, which means now the system, the file system, must decide how to place the data, right? And of course, the goal would be to make a decision, make a good decision, quote, quote. Now, what does it mean to make a good decision? Well, we need to think about what are our objectives? What is the file system trying to optimize for? Well, if we start thinking about it, there are different types of objectives that we can have in mind. First of all, we definitely want to avoid data loss due to corruption or failures, or in other words, we want to maximize fault tolerance of the system. Now, at the same time, of course, we also would like to optimize the overall I/O throughput of the performance. We want to maximize the throughput that the file system can provide for reading and writing these files. Alternatively, we can also think about data balancing as a meaningful objective for a file system. We would like to distribute the data in an evenly way across the different storage media. Of course, load balancing is equally important. We would also like to distribute the I/O request across the different storage media, right? So we can see there are, various different optimization of objectives that we would like to optimize. So for that, and most importantly, some of them are actually competing, right? I could say, hey, I can easily maximize throughput. Let me just place everything in memory. Well, that won't play very well with your fault tolerance objective. Or you could say, okay, I know how to do data balancing. I can just, round robin across the storage media, but that won't give you any guarantees with regards to the load balancing of the system. So in order to address this issue, we have formulated a multi-objective optimization problem where we're actually trying to maximize all 4 objectives concurrently. So as such, we have devised a model for each one of these objectives. So we have an objective function that we're trying to maximize, and then use the multi-objective optimization formulation to try and find a Pareto optimal solution to this issue. Now, formally, the multi-objective optimization objective problem says that we would like to select the best replica location, that is worker tier pairs, for storing a block that optimizes all the different objectives simultaneously. Now, multi-objective optimization is a fairly old problem. There are lots of solutions out there. However, in our case, things are a little tricky because the decision space, that is, the different combinations of worker tier pairs for storing a single file, is actually combinatorial in nature, which means that your typical solutions will run into an exponential running time. So for that, we actually devised a greedy algorithm for finding a near optimal solution to this particular problem. Now, in the interest of time, I won't go into the details of the algorithm itself, but all the details are in the paper. The next is data retrieval, right? A client comes in and would like to read a file. The system must figure out what's the best location to read from, and it does so based on the client location, the replica locations, the network topology, the throughput rates of the storage media and the network, as well as the active connections per worker and storage media. Right? So for this, again, we have devised a model for calculating the data transfer rates from each replica location to the client, so we can select the best one to use. Now, as I said earlier, OctabusFS is a significant extension of HDFS itself, but we kept it backwards compatible with HDFS, which means that it can pretty much be used as a drop-in replacement for HDFS, and taking advantage of the different systems that sit on top and utilize HDFS. Now, at the same time, we also argue that with the API extensions that we've made to OctabusFS, we can now, and the control that it provides, we can now actually go and modify systems on top, like MapReduce or Spark or Hive and so on, to implement interesting optimizations. Right? And I'm going to give you just a couple of examples here just to get an idea. Think about MapReduce, right? Hadoop has a MapReduce scheduler with the list of the map tasks that are waiting to get executed, right? So for each one of these tasks, we know which data, which files are going to access, which means, as far as Octopus FS is concerned, it's like having an oracle that knows which data is going to be accessed soon, right? So with the new API, MapReduce scheduler could actually instruct HDFS and say, hey, this file are going to be accessed soon. Let's just start moving them to higher tiers, right? Other examples come from Hive and Peak about how they're creating different jobs, each job reading the data from the previous job, having short-lived intermediate data, which again are a good candidate for placing them in higher tiers and then deleting them once they're not needed anymore. And we have a few more use cases again in the paper. Now with that, let's move on to the experimental evaluation, which was done on a 10-node local cluster. Each worker node had 24 gigabytes of RAM, 1 SSD drive, and 3 hard drives. Just to get an idea of the performance of the storage media, we have the table here with the read and write throughput, sustained throughput of the 3 devices. And we can quickly see that the SSDs are about 2.5 to 3 times faster than the hard drive, and memory is about 5 to 6 times faster than the SSDs. Now, all the evaluations were done with an array of different benchmarks meant to stress test and evaluate different aspects of the system. In the paper, we have, I think it's over a dozen of different evaluations that we've made. Here, I'm only going to focus on 4 of them. The first one has to do with data placement. So in the data placement scenario, we evaluated our multi-objective optimization policy, or MOP, against the original HDFS using just hard drives, original HDFS using all the hard drives and the SSDs, a rule-based policy that we implemented, and 4 more policies, each one of them implementing one of the 4 objectives that the MOP is actually using. Now, what we see here is that the MOP policy is able to achieve the highest sustainable write throughput per node compared to all the other different policies out there. Just to put some numbers to give some perspective, the original HDFS provides about 80 megabytes per second of per node throughput, whereas the MOP policy can raise that up to about 130 megabytes per second. The data retrieval evaluation compared the Octopus FS policy, which calculates the transfer rates, versus the original HDFS policy, which tries to maximize the location, ignoring, of course, the storage tier information. Now, to make things a little more interesting, we also varied the number of readers we had accessing the data. That's the degree of parallelism that we see here. Because we know that as we increase the number of reads, there are some interesting interactions that are going on. So what we see is that for small degrees of interaction, we see that Octopus FS is able to provide about 3 to 4 times better read performance, which decreases as we increase the number of parallelism, but it still remains better compared to Octopus FS. Now, this decrease in the pattern is due to the network congestion once we start hitting large numbers of readers per node. In the third evaluation, we use the HighBench benchmark for running a series of workloads, different types of workloads, over Spark and Hadoop, And we run it with data both on top of HDFS and OctopusFS. Here I would like to stress out that we did not modify Hadoop or Spark in any way in this setting, right? So we run all the experiments first on HDFS, then we run it on OctopusFS, and the bars shows the normalized execution time. Now for Hadoop, we noticed performance improvements ranging from 10% to 30% to 70%, which is about 3 times faster, but just by simply swapping out the file system. With Spark, the average improvement is about 20%, which sort of makes sense if you take into account that Spark already heavily utilizes memory for its computations. And in the final evaluation, we took Pegasus, a graph mining system that's run on top of Hadoop, and implemented 2 different types of optimization. In the first, we modified Pegasus to detect data that are reused between different iterations and instruct OctopusFS to move that data into higher tier during the workload computation. And then the second optimization was simply placing short-lived intermediate data again to higher tier. And we executed Pegasus over HDFS, unmodified Pegasus over OctopusFS, and 3 times running the 2 optimizations. Now we see that, again, just by simply swapping out the file system, we can get good 20–30% of performance improvements. And then implementing the extra optimizations on top can give us further performance improvements up to about 2x. So in summary, we've built a distributed multi-tiered file system that is aware of heterogeneous storage media, offers both controllability features and automatability features. Now we're actively looking at some automated data replication mechanisms for moving data live based on the workload patterns, as well as some interesting caching policies. And we're also investigating some other enabling use cases across the stack. With that, I'd like to thank you, and I'm ready to take any questions.
So we have time for several questions. Okay, so
So in the first set of experiments, what was the replication vector values that you have used?
Yes. So the replication vector used was the unspecified equals 3, which is the default. Essentially, we didn't specify a replication vector which defaults to 3. And the system gets to decide where to place the data.
Did you try to analyze the automatically decided, like, optimized policies? And is there anything which could be just done manually? Like, for example, it always does 2 hard disk replicas and 1 in memory and stuff like that. Is it? My question is, does it really do things which is hard to do manually?
Mm-hmm. Right. So one of the things that we did was try and implement a rule-based approach, which tries to achieve these objectives as much as possible without doing any math or anything more weird. So it did fairly well. I don't know if you can see the line, this light blue line over here, which still provides good performance improvements over the HDFS, but it was still about 15–20% below what we could do with the MOP policy.
So one more question. So in your higher tier, can you possibly envision using RDMAs?
Yes, I don't see why not.
And so can you a little bit more elaborate on it?
Yes. So as I said, let's put the picture up here. So this picture well, might be a little bit misleading because in reality, we don't really have a memory tier, an SSD tier, hard drive tier, and so on. The tiers are created based on the performance of the actual devices that we have. We have a tool that will do some experiments and it will group the different storage media into logical tiers. So we have tier 1, tier 2, tier 3, and so on. We just give them nice, meaningful names so that people and operators can understand them. So to answer your question, we can easily add any tier we want as long as we can profile it and see what the performance throughput it will give us will be, so that we will know where to place it with regards to the hierarchy. Yeah.
All right, so final question.
Hi, can I ask that for the last experiment that you show against the high benchmark, do you run all of the job together or in isolation? And can you comment on what happened if you run all of them together and the policy sort of like conflicting?
Yes, very good question. So in this experiment, everything is run in isolation because we wanted to study, what's the raw performance improvement we can get. We did run some experiments where we're mixing, randomly the workloads. We still saw similar performance improvements. Yeah. Because the file system, think about it, the file system sits below. It doesn't know if the job is doing a join or a page run or terasort. All it sees is reads and writes. That's it.
All right, so let's thank the speaker. Okay, so the final talk of the session is from Harvard, and Niv is going to talk about their key value store, which is called Monkey.
I need to go to the top. Thank you. All right. Okay. Okay, so hi. So my name is Niv, and I'm a postdoc at the Data Systems Lab at Harvard University. And I'm going to talk about a system that we call Monkey, which stands for Optimal Navigable Key Value Store. And this is joint work with Manos Athanasoulis and Stratos Idreos, who's my advisor. So over the past few decades, the price of secondary storage has gone down at an exponential rate with respect to time. And this led to an increase in the proportion of updates and insertions in application workloads. Overall, these trends culminated in a need for more write-optimized database structures. So to address this need, LSM trees, or log-structured merge trees, were invented in '96. And today, we're seeing an explosion in the number of key value stores that use an LSM tree as a storage engine. So these LSM tree-based key value stores, what do they really look like from the inside? The main design principle that these systems follow is that instead of accessing secondary storage for every update or insertion, they buffer updates and insertions in main memory. When this buffer fills up, they sort the entries by key, and then they flush them as sorted arrays into secondary storage. In order to bound the overall number of arrays that you have in secondary storage, you occasionally merge these runs. And we do this using sort merge operations. Now, because we always merge runs of similar sizes, we have this property that the total number of runs is logarithmic with respect to the input size. And these runs are exponentially increasing in terms of sizes. In order to handle a lookup to find a given key, we first of all start by probing for it in the buffer, and then we search different runs from smallest to largest. And we have these fence pointers in main memory, and the job of these fence pointers is to contain min-max information about every key and every disk page of every run, and they allow us to access each run using just one disk I/O. In addition to the fence pointers, modern systems also store Bloom filters in main memory to probabilistically allow you to skip probing runs that don't contain the key that you're looking for. And these Bloom filters might return a true negative, which is great for performance because we skip probing a run that doesn't contain what we're looking for. They might return a false positive, which is not so good for performance because we waste one I/O probing something that doesn't contain the key that we're after. Or they might return a true positive, in which case we find what we're looking for and the lookup terminates. So there's some interesting performance and cost trade-offs in this space. In particular, the bigger we set the Bloom filters to be, the bigger we set the Bloom filters to be, the fewer false positives we get during runtime. And this reduces the number of IOs that we have during runtime, and so performance improves for lookups. And so this gives us a memory versus lookup cost trade-off. Moreover, the more aggressive we are about merging runs during runtime, the less runs we actually have to probe during lookups, because there's simply less runs in the system, but that also increases the amortized cost of updates. So that gives us a lookup cost versus update cost trade-off. Okay, so we see that we have these three cost and performance metrics: main memory, lookup cost, and update cost. And the question is how to trade off between them in a realistic system. And to help us answer this question, we can actually visualize the space. So we can visualize a projection of the space in 2 dimensions, the trade-off between lookup cost and update cost. So for a fixed amount of main memory, we can say that existing systems fall upon a trade-off curve between lookup cost and update cost. We can navigate this curve by merging less or merging more. And we can shift this curve up and down by allocating more or less main memory to the system. Okay, so we address 2 problems in this space that we identify. The first one is suboptimal Bloom filters allocation. So in particular, we show that for a given amount of main memory, there is a trade-off curve that we call the Pareto frontier. We define that as a curve beyond which lookup cost cannot be improved without harming update cost, and vice versa. And for a fixed amount of main memory, existing systems are not tuned along the Pareto frontier. And we show that the reason for that is that they don't tune the Bloom filters optimally with respect to the worst case lookup cost. The second problem that we address is tunability. So we show that these systems are quite hard to tune. In particular, what would be the impact of adding or taking away a given amount of main memory from the Bloom filters on lookup performance? This question is hard to answer today. Moreover, how do we want to set the greediness of the merge policy to strike the perfect balance between update cost and lookup cost that maximizes throughput for a particular application? So we address these problems with Monkey, which stands for Optimal Navigable Key Value Store. So Monkey addresses these problems using the following observation, insights, and steps. Firstly, we observe that in all existing key value stores, the Bloom filters are all allocated with a fixed false positive rate. Our observation is that lookup cost, or the total number of IOs that you waste due to false positives during a lookup, is proportional to the sum of the false positive rates over all the Bloom filters. Yet setting the same false positive rate to all Bloom filters doesn't minimize the sum, and so it doesn't minimize lookup cost. So we show how to allocate main memory among the different Bloom filters so as to minimize the sum of their false positive rates and thereby also minimize lookup cost. And we show that if you do this optimization, lookup cost actually becomes asymptotically better. So we'll see how. And furthermore, we develop a model that allows you to trade off precisely between the amount of main memory that you allocate to Bloom filters and what lookup performance is going to be. Secondly, is the navigable aspect of Monkey. And our observation is that in modern key value stores, it's difficult to set a given merge policy and predict what performance is going to look like. Our insight is that an LSM tree using just a merge policy can be tuned to assume any performance characteristics from those of a write-optimized log to those of a read-optimized sorted array. And so the merge policy is very critical for performance. And so it's very important to optimize that for a particular application workload and hardware. And so we show how to map the tuning knobs that control the merge policy onto the space of performance characteristics and how to navigate that space for a particular application. Finally, overall, we show that existing key value stores strike an ad hoc and suboptimal trade-off among main memory, update cost, and lookup cost. We show that due to the Bloom filters optimization, Monkey exists on a better trade-off frontier than existing systems. And furthermore, it's able to navigate that frontier by tuning the merge policy in order to find the best spot for a particular application. And we can also use our framework to answer all sorts of what-if questions. Say, what happens if we change the hardware, the workload, the data size? What would happen to performance? OK, so now we start off with the optimal part of Monkey. That is the Bloom filters optimization. So we go back to the architecture of a modern key value store. And we observe that there are 3 different data structures in main memory: the buffer, the Bloom filters, and the fence pointers. And the question is how to allocate a given budget of main memory among these 3 different structures. Now we observed that in real systems, the Bloom filters actually take up most of the main memory. And so we narrowed down the question on just how to set a given main memory budget to the Bloom filters. Now, existing systems set a fixed number of bits per entry to every Bloom filter. So this means that the size of every Bloom filter is proportional to the size of the run that it corresponds to. Now there is a famous Bloom filter equations that relates the false positive rate of a Bloom filter to the number of bits per entry that we set to it. And based on this equation, because we set the same number of bits per entry to every Bloom filter, it also means that all the different Bloom filters have the same false positive rate in existing systems. Now, with respect to just this design, can we quantify the worst case lookup cost in terms of IOs during lookup that don't actually do any useful work, that probe runs without finding the key that we're looking for? And the answer is yes, we can. So the expected number of IOs that we waste during a lookup due to false positives is just probabilistically the sum of the false positive rates over all the different Bloom filters. Now, the false positive rate is equal to e to the power of your number of bits per entry. So we can extend this equation and replace p by this expression. And because we have a logarithmic number of Bloom filters in our system, because we have one Bloom filter for every run, we can also replace the sum notation by the log term. And so we have this expression. And the question we ask is, can we do better than this? OK, so the key insight is as follows. The real worst case scenario for these systems is when we issue a lookup for a given key, and the Bloom filters return a false positive for every single run. This means that we have to issue one IO to everyone in the system. And that's our worst case performance. And the key observation here is that most of the main memory in the system is allocated to the largest Bloom filter. And the reason for that is that the sizes of the runs are exponentially increasing. And so, and the sizes of the Bloom filters are proportional to the capacities of the runs. So most memory is just at the bottom. And you can see that each one of the runs might contribute to one IO during runtime, but most of the main memory in our system is saving us at most one IO. So that's something to be suspicious about. So what we do, or the intuition behind the optimization in Monkey, is that we take some of the main memory from the largest Bloom filter, and we reallocate that to some of the smaller Bloom filters. That's going to cause an increase to the false positive rate of the largest Bloom filter, but it's going to cause a decrease to all the false positive rates of all the other Bloom filters that more than offsets that for the total sum of false positive rates. And so that's going to overall cause a decrease in lookup cost. And that's exactly what we do in Monkey. So with Monkey, with the same amount of main memory, you issue fewer IOs per lookup on average. And we achieve this optimization using the following 3 steps. So first of all, we relax the constraint that all false positives should be equal to each other. So we say that any false positive can be anything between 0 and 1. Next, we create a model for lookup cost and the total main memory footprint for the Bloom filters with respect to these false positive rates. And finally, we optimize these expressions with respect to each other. And we do that in terms of the false positive rates, which are now just variables in our optimization problem. So let's break this down into a bit more detail. So here are our false positive rates, and we know that lookup cost is proportional to the sum of their false positive rates. Now, we can derive the total main memory footprint from the system by, again, using our Bloom filters false positive rate equation. We can just rearrange this equation to be in terms of bits. And now we can apply this equation separately for each one of the Bloom filters in our system. Then we can actually, if we sum up the total main memory for all the different Bloom filters, we can derive an equation for the total main memory for all Bloom filters with respect to just the false positive rates that we assign to each one of the Bloom filters. Okay, and now we have 2 equations for lookup cost and total main memory footprint. Now we can optimize these equations with respect to each other. And this becomes a multivariate constrained optimization problem, which we can solve using standard optimization techniques. And we use Lagrange multipliers in the paper, and the derivation is all there. So the main result is as follows. The optimal false positive rates that minimize the sum of false positive rates and thereby lookup cost should be exponentially decreasing for smaller runs. Right? And this is in contrast to the state of the art that assigns the same false positive rate to every run. Okay, so if we make a comparison of these 2 schemes under the same main memory footprint, we'd see the following. The false positive rate for the largest Bloom filter in Monkey is going to be higher than for the state of the art, but the rest of the false positive rates for all the other Bloom filters will be lower. And overall lookup cost will be lower. Okay? And what we actually observe when we break down these expressions is that Monkey actually shaves a logarithmic factor from the asymptotic lookup cost performance. And so Monkey, sorry about the thing at the bottom. So we have an asymptotic win. And so lookup cost scales at a slower rate with respect to the data size. Okay? And the intuition for this asymptotic improvement is the following. It's that the false positive rates basically form a geometric series that converges to a constant. Right? So that eliminates the log factor. Now, what we can also do is we can take these false positive rates, these optimal false positive rates, and plug them into our equation for the total main memory footprint. And that gives us an expression for total main memory for the Bloom filters with respect to a given desired lookup cost that we want to guarantee for our system. So this gives us a model for lookup costs versus main memory. And so this kind of equation can allow practitioners to exactly determine how much main memory to assign the system to guarantee a particular performance guarantee. Okay, so now we take a quick pause and we go back to the problems that we'd set up at the beginning of the presentation, and we look at how well we've addressed them so far. So we've addressed the problem of suboptimal filters allocation using this optimization, and so this allows existing systems for a fixed amount of main memory to be tuned along the Pareto frontier. Right? So this just allows you to dominate existing systems for any tuning. Now, with regards to the second problem, we've also derived a model that allows us to trade off between lookup cost and main memory footprint. And so now we can do that. What we will now do is we'll address the problem of how to set the merge policy of the LSM tree to find the perfect balance between update cost and lookup cost for a particular application. All right, so we move on to the second part, the navigable part of Monkey. So we do this part in 3 steps as well. First of all, we identify the tuning knobs that control the greediness of merge operations in an LSM tree. These are the merge policy, what we call the merge policy and the size ratio, and we'll see exactly what they mean. Then we map the impact of these tuning knobs onto the space of performance characteristics. So we're basically going to show how to derive this curve. And in particular, we're going to show that an LSM tree can be tuned as anything between a write-optimized log all the way to a read-optimized sorted array. So an LSM tree is a log, a sorted array, and anything in between. And so these data structures actually come to be at the extremes of the spectrum. And finally, we're going to show how we can actually navigate the spectrum for a particular application workload and hardware configuration to find the best spot. All right, so there are 2 merge policies that we need to know about for an LSM tree. These are called tiering and leveling. Tiering is more write-optimized, and leveling is more read-optimized. So let's see exactly what they look like. So with tiering, whenever a run flushes from one level to the next level, we just continue accumulating runs in a given level. And only when that level runs out of capacity, we merge all the different runs in that level into one, and then we flush that run into the next level. With leveling, we're much more aggressive about merging. So whenever a run flushes to the next level, we immediately trigger a merge operation and enlarge the existing run at that particular level. So it looks like this. Now finally, when the given run at a level exceeds the capacity of the level, only then we flush that to the next level. And so this gives us a few performance guarantees. So in particular, under tiering, we have T runs per level, where T is the size ratio between runs. And with leveling, we have only strictly 1 run per level. And now we can actually analyze lookup cost with respect to these 2 different merge policies. So under tiering, lookup cost is equal to T, which is the number of runs per level, multiplied by log of n, which is the number of levels, multiplied by the false positive rate. For leveling, it's exactly the same, except for we don't have the T because we only have 1 run per level. And the impact of Monkey, as we showed before, is to eliminate the log term. So Monkey eliminates the log factor under both of these schemes. All right, so we get the following. Now, we can also analyze update cost with respect to these 2 merge policies. So under tiering, every entry participates in 1 merge operation per level. And that means every entry participates in just a logarithmic number of merge operations with respect to the input size. And so update cost is log of n. And for leveling, every entry participates in at most T merge operations per level before getting flushed to the next level. And it overall goes through log of n levels in total. So our update performance is T multiplied by log of n. All right. So we see that these performance characteristics are highly dependent on the size ratio T. And so it's interesting to analyze what happens to these characteristics as we vary t, from being very small to being very large. So as we decrease t, what we observe, if we just look at these expressions, is that they actually converge. So that shows us that the performance of a tiered allocentric and of a leveled allocentric converge when t is very small. And actually in the paper we show that when the size ratio t is equal to 2, they actually they behave exactly the same. Now, let's see what happens when we increase the size ratio beyond, as the size ratio becomes really, really large. As the size ratio becomes really large, what happens is that the first level in the allocentric becomes so large that the capacity of the data never actually exceeds it. And so we just have one level. And that means that with tiering, we never actually get to merge. So we just accumulate runs in a particular level. And so a tiered allocentric degenerates into a log in this case. And a leveled allocentric, it just has one run in that level. It never exceeds the capacity of that level. So whenever the buffer flushes, we merge that into that one run in that level. And so a leveled allocentric degenerates into a sorted array. Okay, and so if we map that into the space of performance characteristics, we get the following. We observe that when the size ratio t is very small, the performance of tiering and leveled allocentrics is the same. But as it increases, a tiered allocentric becomes a log, and a leveled allocentric becomes a sorted array. And now we have the spec. So I want to drill this in. An allocentric is a log, an allocentric is a sorted array, and an allocentric is anything in between. And now we can actually map these tuning knobs onto this performance continuum, and we can just navigate that to find the best spot for a particular balance between updates and lookups in a workload, or a particular cost ratio between reads and writes on a particular hardware. And we can just find the best spot that maximizes throughput for our application. All right, so now we've also addressed the second part of the second problem, namely how to find the perfect merge policy for a particular application scenario. Okay, so we implemented Monkey on top of LevelDB to evaluate performance. And in this experiment, we show what happens to lookup cost as we increase the data size. And as we increase the data size in this experiment, we actually increase the size of the Bloom filters in proportion. Right? And what we see is that lookup cost for LevelDB increases at a logarithmic rate as we scale the data and Bloom filter size in proportion to each other. But in Monkey, it stays fixed. So in Monkey, as long as we scale the Bloom filter size in proportion to the data size, lookup cost remains fixed. And that demonstrates the asymptotic superiority. Moreover, we ran an experiment where we varied the proportion of lookups and updates in the workload to demonstrate the adaptive capability. And we show that we compare two versions of Monkey to LevelDB. In one of them, in the fixed version, we don't navigate the merge policy. And in the top version, the navigable version, we do the Bloom filters optimization and the navigation. And we see that it takes a navigation of both of them to really maximize throughput for a particular application. Okay, so our project Monkey is within the largest framework of a project that we're working on at the Data Systems Lab called CrimsonDB. CrimsonDB is a new key value store that navigates the design space to that navigates an even broader design space than Monkey to find the best spot for a particular application, and is also able to answer what-if performance questions. So stay tuned for more about CrimsonDB. And Monkey is the first iteration in CrimsonDB. All right, so overall, we've shown that existing systems strike a suboptimal and ad hoc trade-off among lookup cost, update cost, and main memory. We've introduced Monkey that addresses these problems through two steps: the Bloom filters optimization and navigating the merge policy. And we have a bit more in the paper. We show how to allocate any amount of main memory among different in-memory data structures. We also address skewed and range lookups. We have this website that offers an interactive demo of all the models in Monkey. So you're welcome to go there and change different parameters and see the impact on performance. And thank you very much for listening.
Okay, so we have time for a few questions.
So when we use the explicit block cache, or we implicitly use the OS buffer cache, Bloom filter miss does not necessarily mean that we need to I/O on the disk.
Yep.
And I was wondering how would that impact the formula that you presented here?
Yeah, so you're absolutely right about that. So the impact of that, so when many of the runs are in main memory, there's a negligible overhead of querying them. to model this scenario using the models that we have here, what you would effectively do is enlarge the buffer size to be as large as all the data that actually fits in main memory. That basically simulates the case where a bunch of your data is in main memory. And so we're only modeling performance for IOs to these runs that are in secondary storage. But actually, we also have experiments with a block cache in the evaluation section. So you can look at those. And we show that the cache actually has an orthogonal impact. So Monkey still dominates even when there's a cache. And the cache is still going to benefit performance when you have a skew in your workload. And yeah, so thanks for the question.
Hi, I'm Scholt from ETH3. So very cool stuff. My question is related to the, let's say, the changing cost ratios as the system is evolving. So when you start out with some amount of data and you choose the optimal Bloom filter sizes, and then you ingest a lot more data, which might reside in other tiers, like for instance, movable in memory, then suddenly you might be using a lot more space for your Bloom filters that you ideally should, because you chose a number of bits per entries to be larger to avoid the problem. You get my point. So my question is, is there a nice way of dynamically rescaling these? Is there an overhead associated with it? Or is it actually a non-issue and I just didn't catch it?
Yeah, so if I understand correctly, maybe you can actually keep the mic, but if I understand what you're saying, basically you're asking what happens as the data size grows, whereas the main memory budget stays fixed.
Yep.
Yeah, okay. So when that happens, I mean, lookup performance here is dependent only on the ratio between the total number of bits for all filters and the number of entries in your system, right? So so lookup cost, if in that scenario, lookup cost is actually going to increase as the size of the data grows, but it's going to increase at a slower rate. And so the way to fix that is, as we showed in, I'm not sure the clicker is working, but as we showed in one of the performance graphs above, is as long as you scale the total space for the Bloom filters in proportion to the data size, your lookup performance stays fixed. Whereas in the state of the art, it still increases at a logarithmic rate, right? So that's what we do. We cannot keep lookup performance good if we have very, very little main memory compared to the data size.
So great talk. So question, in the common case where you have data being overwritten and then your newest data is going to be stored at the highest level, then of course you don't actually end up needing to check lower levels. So then doesn't the true positive rate also impact what you would want your Bloom filter size to be?
So you're saying that if some of the more recently updated entries are also looked up more frequently.
If some of the entries are overwritten more frequently and are more likely to be at higher levels per tier, then it seems like that would affect what you would want the size of your Bloom filter to be, only because a false positive at a lower tier isn't going to matter if you never need to check that tier because you find the data earlier.
So I mean, yes and no. I mean, if these lower runs are actually in secondary storage, we're still going to have to issue IOs to these runs. Now, it's true that on average, if the entry we're looking for is at a lower level, it's true that we have to issue less IOs to find that entry, but we still have to issue those IOs. And that's a problem for performance. And so actually, even in that case, the Bloom filter optimization here helps you quite a lot, because we set the false positive rates for the lower runs to be very, very low, which means that with Monkey, even for this kind of workload, this kind of skewed workload, your performance is actually going to be much better as well. So Monkey addresses that scenario very well as well. We have experiments in the evaluation that actually shows what happens as you vary temporal locality for lookups. Thanks for the question.
So I think we're out of time, so let's thank the speaker and
Thank you so much. Appreciate it. Thank you. Okay, yeah.